And with that, I'm going to introduce our next speaker from my own lab affiliate, Amanda Navine. Her talk is Advancing Endangered Hawaiian Bird Species Monitoring using Bioacoustics and Machine Learning. So without further ado.
Can everyone hear me okay? Okay, great. So, aloha, everyone. As Noah said, my name is Amanda, and I work in the Observatory for Hawaiian Ecosystems here at UH, better known as the Lohe Lab with Dr. Hart. I'm an acoustic bioinformatics specialist, which is just a fancy way to say I listen to birds all day and try to make some scientific inference from their songs. I'm going to be telling you about our project to advance endangered species monitoring using bioacoustics and machine learning. So specifically, we are trying to develop better tools for monitoring bird species that are native to the Hawaiian Archipelago. As you may or may not already know, Hawaiian birds are some of the hardest hit taxa in the world when it comes to extinction rates. It's estimated that over 68% of Hawaii's birds are already lost. The conservation of our remaining bird species requires accurate understanding of their population trends and their responses to our conservation action. However, monitoring many of these species is often difficult for several reasons. First, many of these species persist in difficult to access habitats, such as dense, wet, high elevation forests that are only accessible by helicopter, or remote Rocky Mountain summits where seabird burrows are almost indistinguishable next to lava. Second, conservation budgets are often tight, and conservation biologists are busy people. It's just not logistically practical to be getting scientists and field biologists up to these remote sites to do frequent surveys. Oftentimes, surveying critical habitats only occur once or twice per year, or in some cases, only once every 5 years. Over this period of time, bird species can decline rapidly and without warning, as was the case with Akikiki on Kauai recently. It's estimated that the Akikiki over the course of 3 years dropped from an estimated 440 individuals to less than 100. This is a pretty shocking decline. And if they had more monitoring, you may have been able to catch this decline a little early. Lastly, a lot of these populations are at such low densities that if a surveyor is unlucky, they may not catch this bird species on account at all. For these reasons and others, passive acoustic wildlife monitoring techniques have become increasingly popular. Automated recording units, or ARUs, as pictured here in the center, can be deployed in difficult to reach habitat and left for days to months to record stick data, which can then be analyzed to track population trends continuously. So while this is a really appealing option for us, it's not without its own challenges. These ARUs can collect vast libraries of soundscapes, and you can ask any member of the Lohe Lab going through each soundscape spectrogram, like pictured here on the bottom right, and manually annotating it for your species of interest is tedious, time-consuming work. There's just more data collected than can be reasonably analyzed in a reasonable amount of time. And that's where machine learning comes into play. Recent advances in machine learning have made it possible to automatically detect bird song from sound signals, which greatly reduces analysis. Such automated detection algorithms have been wildly successful for common bird species. For example, BirdNet, the algorithm that we work is capable of identifying over 3,000 remote common species. BirdNet was developed by the Cornell Lab of Ornithology, led by Stefan Kohl, and it is a deep neural network, which is trained to identify species-specific patterns in spectrograms in order to identify which birds are singing and recorded. So this seems like the exact tool that we need to solve our data analysis problem. However, deep neural networks are data-hungry models. They require hundreds, if not thousands, of spectrograms to be able to make robust predictions. This means that models such as BirdNet lose predictive powers for species that are underrepresented in acoustic libraries such as the Canto or Macaulay Library. Unfortunately, island species are chronically underrepresented in such databases. This is especially true for rare and endangered species. So while BirdNet is a really powerful tool in human systems, the lack of training data for Hawaiian species makes it very limited in its potential. So over the past year, I have been collaborating with Cornell Lab of Ornithology to expand BirdNet's potential to Hawaii and make this tool available for our conservation biologists. So to overcome our inability to train a deep neural network without ample training data, we've adopted a couple of different tactics. First, we hosted an international coding contest called BirdClap 2022. The mission of this contest is to globally crowdsource innovation for improving automated detection algorithms with little data. While we had over 1,000 participants worldwide, the overwhelming majority of models that were submitted for the contest used the same model architecture used by BirdNet. So we didn't really get any new material from it. It was quite surprising to us that very few other forms of machine learning were submitted, and those few that were submitted did not perform particularly well. However, we did gain a few insights. First, interestingly and surprisingly, the number of training recordings that we provided per species only loosely correlated with model performance. So in this scatter plot, we have the log-based number of training samples that were provided for each species on the y or x-axis. And on the y-axis, we have model performance metrics. And we can see that with the number of training samples increasing, we do see an increase in performance, but the association is not very tight, and it doesn't increase as much as we might have expected. So this suggests that other factors, other than the quantity of acoustic data, may be shaping model performance. In this plot, we have a handful of species that we highlighted during the context on the x-axis, and we have, again, model performance on the y. So these are only the scores for the top 5 scoring teams. And we can see that scores vary wildly between the species. In parentheses above each one is the number of training samples that were provided for that species. So some of them, like the Amakiki, look like they were fairly easy to train into the model, whereas other species perform pretty terribly. So why is this? Well, if you look at the Akiapola'au and the Akeake, for example, you can begin to tease apart some of the other factors that might be influencing the model. The Akiapola'au is a honey creeper that inhabits the wet native forest here on the Big Island, where several other species of honey creepers, as well as non-native species, can almost constantly singing. The Akeake, on the other hand, nests in the remote lava flows of the summits of the mountains and mainly only vocalizes at night, when vocalizations from other species are practically non-existent. You can ask anyone who's trying to learn how to sing bird songs. You learn it a lot faster if you don't have other birds singing over it. Seems to be true for machine learning algorithms as well. Further, the Akiapola'au has a distinctly finchy quality to it. It has a similar frequency band as many other species, and is in these really dense forested habitats where it can be hard to hear at any distance. To the untrained ear, that call could be mistaken for a house visual. The Akeake, on the other hand, have a very distinct, almost guttural call that is difficult to mistake for other species. I'm not sure how well you were able to a little bit more. So taken together then, it's maybe not surprising that a machine learning algorithm would struggle to identify an Akiapola'au from a soundscape, but it wouldn't struggle with an Akeake. So things like habitat characteristics, vocal complexity and repertoire size, similarities between species, etc., can be shaping model performance, and we need to consider that as we move forward to try to develop this. So because our coding contest did not reveal any brilliant new innovation for training a model without substantial training data, we went about collecting more training data. But this time, instead of starting from scratch and manually going through each soundscape to find our rare species, we took advantage of a machine learning training technique called validation. We took fresh soundscapes that BirdNet had not been exposed to previously and allowed it to make predictions. We then took these predictions and said, yes, you are correct, or no, you are incorrect. These correct and incorrect predictions from BirdNet were then fed back in as further training data. Through this series of validations, we're able to improve its performance and give it specific feedback on those tricky species like the Akiapola'au. So this quickly and exponentially increased our sample size. And within just a couple of weeks, we hope to have a new and improved model for Hawaii. We're working on a model that is unique to the island species instead of having all of the global species included. Once we have this tool under our belt, we plan to use point counts conducted here in Hawaii as ground truths for developing a method for making accurate occupancy models and density estimates for species using a single ARU. So up until this point, arrays of multiple ARUs have been required in order to make such density estimates. For our single ARU methodology, we vastly increase the amount of area that we surveyed for projects on a budget. We also intend to expand our bioacoustic analysis services to managers and researchers who want to get a better idea of the bird population trends in their areas. And for example, we intend to have grades of ARUs deployed in areas that are planned for landscape scale mosquito control. We're really excited to bring this revolutionary tool to the islands. We think it's going to be extremely helpful for population management. We're going to be able to sample at the community level on an archipelago-wide scale at finer tinfoil resolutions than ever before. So it gives us a better understanding of how bird populations are responding to climate change, land use change, and importantly, our conservation mission. This has been a huge project to develop this tool, and I want to thank everybody that is here, as well as all the organizations that have supported us. And with that, we'll take any questions.
Distinctive model, which doesn't include a lot of the mainland species, might confuse the AI.
Yeah, so there's a bit of a conflicting theories there. So on the one hand, it helps us not to have too many species in the model, because then we have to come through a lot of false positives. So if BirdNet is making many predictions for birds that aren't possible here, that's just more data for us to have to sit. However, having more species in the model gives BirdNet a process of elimination. It says, oh, I know what this bird sounds like, and so I know it's not that. But if that bird is not trained into the model at all, it doesn't have that way of eliminating that key. Does that make sense?
Yeah, so maybe you keep that and you weight it lower.
So what we're thinking is keeping that, and then only in the very last step, having it only report the birds that are possible. So it's trained on all of the species, but then in the end, only the species that are possible are selected from that list to be reported.
You don't want to keep that in there just to monitor for new arrivals?
It's just
Is the sacrificing performance that?
I think it depends on your question. It depends on your specific research interests. I do think that for landscape scale monitoring of whole communities, it would be good to see if these species come up. So the model produces species estimates as well as confidence scores. And so you could maybe keep the confidence threshold for those birds pretty high to weed out a lot of the false positives, but still double check it if there is that bird. You can go back into the data and look at the segment that was generating that prediction and say, oh yes, that's right. There's a new bird here. We should maybe go look at it. But yeah, I think that the way you would go about that is having the confidence level quite high for birds that aren't.
I've got a question, Amanda. So one of the issues with training this model is that we have extremely low sample sizes for critically endangered birds. However, like Ant's photo here shows, we do have some of those critically endangered birds at KBCC or MBCC. So would it be possible, I don't know if these birds sing much in captivity, but could we use recordings from
I've asked
those locations to help train the model? And are there maybe significant differences between captive bird songs and wild bird songs that create problems for the model?
Very likely, actually. One of the major problems with having with the model is that we have a cultural convergence of birds, especially on Hawaii, where many of the Hawaiian newspapers that are left sing their similar songs. And because they don't have any conspecifics to learn from, their songs are getting closer and closer together. And so one problem we're having with Hawaii is being able to distinguish which honey creeper is singing. The bird net can't tell, we can't tell, without more visual clues. So one thing we might have to do in that case is have like a category. So in Hawaii, instead of saying, oh, that's an ani owl, that's an kihi, or whatever birds are being confused, we have a category that, oh, that's a honey. In order to make sure we're still getting low red inclusion, but not overestimating which. But yes, I would love to have aviaries loaded with ARUs and get all that data. It's in the works, I hope. Thank you.